This is Matt Beattie, and I am recording this video to show you how my Cuisines program works. This is project 2 for DSA 5970. So we'll start off, we're in my SSH session, and you can see that I'm in my projects directory, and we're going to take a look at the Cuisines project. So we'll first take a look at the tree structure. As you can see, it's a typical Python tree structure. We've got a README file, the main cuisines area, our documents, which would include our recipes from yumly.json, and then some other information files. And then these are important. It includes classifiers as pickle files and training and test data, which are feature extracted files that include vectors, which we'll look at in a second. But again, those are included as pickle files so that you can actually use the program without having to create the classifier each time it's run. So let's go take a look at the README file first. So the README file includes just a simple overview that says that Cuisines is a module containing a set of functions in one main program that's used to determine recipes and cuisines when given a set of ingredients by the user. This program has a little bit more error checking than the redactor program because I've gotten better at programming Python, quite frankly. So this one, although the instructions say to copy it to a projects directory, you can actually install this tarball anywhere you want to. Again, this is an installable module so that the functions can be used in any program once you put it in. And it talks about the main files that are installed here. So we've got cuisines.py, the classifier pickle file, training data, and test data pickle files. These are the largest because they include feature sets, a documents directory, yumly.json, and our test files. Testing's done with PyTest. We're going to do that in just a second. And then you can see here the options for running cuisines.py. You can choose whether or not to make use of the pickle files. For the purposes of this video, we're going to do that. You can tell it whether or not you want it to generate new feature sets. So for example, if we actually wanted to use the feature sets but generate a new classifier, we could include both the pickles and the features options so that we could, if we want to generate features and classifiers, we would put both of these options in here. If we actually wanted to use the existing classifiers, or we wanted to create classifiers and not create feature sets, then we would leave out both options. If we want to use the existing classifier, we do indeed want to use the pickles options. So the train count and test count flags are used to set the number of recipes to create features for both training and test. The classifier generates a new classifier, and so if this option is not included, it will use the existing pickle files, and it generates a classifier using either naive Bayes or decision tree and selects the one that works the best. And then finally, the ingredients themselves, like this is for the general user, would be just using the Cuisines program and including ingredients. That's what we'll demonstrate here. The way this works is that cuisines.py uses the scikit-learn package for most of its analyses. What I did was I took the yumly.json data and read in all the ingredients into a set, and then for each recipe, read the recipe in from the JSON file, and then created a binary vector of features that represented the presence of each one of the 6,174 potential ingredients. So for example, if it was to create, take a recipe that had 3 ingredients, water, salt, and pepper, the feature vector would include 6,171 zeros, and then would include a 1 in the location for water, a 1 in the location for salt, and a 1 in the location for pepper. Feature creation was by far the most time-intensive portion of this program. With the features created, then Cuisines calls the naive Bayes and decision tree classifier construction methods in scikit and uses those to generate a classifier. With our classifier in hand, we can then analyze the ingredient sets supplied by the user, identify which cuisine the user is most likely to want to create, and then we then look for the recipe in the JSON database that is closest to what the user would most likely use the set of ingredients for. And this routine, we use KNN clustering, again from the scikit package. So we're basically taking the vectors associated with the recipes and looking for the ones that are closest to them. So the way the program performs well in execution, but in preparation, it's extremely slow and uses a great deal of memory. The feature creation is by far the longest routine involved here, and so we had I used about 3,000 training recipes. So to generate the feature matrix, if you will, we have n number, as in the number of training recipes times 6,174 comparisons to create the binary vector. So it's not a very efficient program. It could become more efficient with some better means of executing the program. As I mentioned in one of my previous videos, Python does not take advantage of multiple CPUs unless you put in some multiprocessing routines. Probably the easiest way to improve the performance of this program would be to run it on a Spark cluster, which would automatically do that for us and increase the number of recipes used in classification. But even so, it works pretty well. So the first thing we'll do is we'll run a PyTest on it. And you can see we got an error here because it was looking for a UJSON module, which is not included in my Python version 2 library. So we need to use Python 3. And it should work. And it does. So we have 3 tests here. We find 3 different cuisines, and you can see that it passes the 3 different cuisines, and it has tests set up to determine what the closest recipe for the ingredient set provided by the user is, and it passed there too. So since it passed, it doesn't supply us a ton of detail. Let's go ahead and take a look at the test cases. So we can see what happened here. So again, you can see that it calls the pickled classifier, pickled training and test data, again, because we don't want to have to recreate that because it would take forever to run the test. And then we look for cuisines. So we'll explain the first one. So we give it feta cheese and pita bread. Well, feta cheese and pita bread are common ingredients found in Greek food, specifically if you wanted to make gyros. So it looks for Greek, which is indeed the output that it gets. Down here in the nearest neighbor checks, we give it a set of ingredients, in this case tortillas, habanero, pepper, and chilies, and we would expect it to find a Mexican recipe, in particular recipe 2239 from the JSON set. And again, using these pickled classifiers and training and test data, everything worked okay. So with that, we'll go ahead and demonstrate the program itself. And in this case, we will give it Let's see here. We'll give it an Italian set of ingredients. We'll put in oregano. That's pretty common. We'll put in Parmesan cheese. And we'll put in pasta. And again, we need to tell it to use the pickle files so that it doesn't try to create a new classifier. And you can see the output here. So the first thing it does is it reads the recipe files from yumly.json. It does that every time, just so I can kind of look at some of the stats. And in the Yumly database, it has 20 cuisines, 39,774 recipes, and 6,714 unique ingredients. So the output of interest to the user starts here. It says your refrigerator, so that's what's in their refrigerator, has oregano, Parmesan cheese, and pasta. And it checks for matches in the ingredients list in the 6714 with mine. And lo and behold, it found the matches. I'll show you what happens when it doesn't. So it looks for recipes with oregano, Parmesan cheese, and pasta. Uses the pickle classifiers, and then comes back and it outputs the 5 most likely cuisines. So we can see Italian 94.4%, Mexican 4.5%, then the others drop way off, Cajun, Southern, and French. The top 5 most likely recipes are listed here, where we can see smaller distance would mean closer. So recipe 1397 is the closest recipe to what we would expect for the set of ingredients our user has. Now let's run it and make it not find an ingredient. So we'll do the same thing. Let's give it oregano again. Give it pasta. And let's give it something that we wouldn't expect it to find, like a stapler. Oops. I misspelled ingredient. Which is fine because we want to make sure that we include that pickle file option. There we go. And so up here you can see a little bit of error handling. So it says your refrigerator has oregano, pasta, and stapler, and it couldn't find stapler in the 6714 ingredients. So it says you may want to try re-entering, but we'll skip it for now. So we just use oregano and pasta. Again, Italian comes up as the most likely cuisine, but you can see that the probability of Italian went down from 94% down to 50 to about 60%. And of course, we have a different recipe now. So everything seems to be working pretty well, quite frankly. So this routine did indeed do what we expected it to do. We could improve its performance by doing more recipes. Again, that would be best run on a Spark cluster. But other than that, the program does indeed work pretty well. So with that, we'll end this video.